Hi everyone, welcome back to the second session on finite element analysis of beams. In this session, we are deriving the stiffness matrix for the beam element. Now, the learning outcome for this session is to derive the stiffness matrix for the beam element. Now, the stiffness matrix for the beam element is derived by considering the strain energy equation, and this is the strain energy equation we derived under strain energy chapter in the mechanics of material. That is given by strain energy is equal to integration over the length of the element m square divided by 2ei into dx. Now that m is the applied moment and ei is the flexural rigidity of the beam. Now I need to replace the m in terms of differential equation that is given by differential equation of deflection, that is 1 by r is equal to m divided by ei, that will be equal to d square y divided by dx square. That is the equation of deflection we are derived in mechanics of material under deflection of beams. Now here if I rearrange the terms, I'll get m is equal to ei d square y divided by dx square, and that will be equal to ei d square v divided by dx square, where y is the deflection in the beam and in FEM the y will be replaced with v. Now this value of m I need to substitute in equation number 1. When I substitute that value of m in equation number 1, I'll get this modified strain energy equation. Therefore my strain energy is equal to integration over the length of the element. So now m is replaces with ei d square v divided by dx square whole square, because I have m square here. So this term whole square divided by 2 ei as it is into dx. Now I'll apply this square to both the terms here. Therefore it is ei square into d square v divided by dx square whole square divided by 2 ei as it is into dx, and that will be equal to, here 1 ei and here 1 ei will be get cancelled, left out with 1 ei into d square v divided by dx square whole square divided by 2. Now if I take that ei 1 by 2 and this ei outside the integral, this is 1 by 2 ei integration over the length of the element d square v divided by dx square whole square into dx. This is what my second equation. Now we have the relationship between local coordinates and the global coordinates, that is given by zeta is equal to 2 into x minus 1 divided by x2 minus x1 minus whole term minus 1. This is the relationship we obtained in the previous sessions between the local coordinates and the global coordinates, where x2 minus x1 is what my length of the element, that it is shown in the next diagram. Therefore so x into x minus x1 divided by length of the element minus 1 is what the relationship between local coordinate, that is zeta, in terms of global coordinate, that is x. Now when I differentiate this zeta with respect to x, I am going to get this. So it is differentiating with respect to x, 2x is 2, and differentiating 2 into x1, it is constant, becomes 0 divided by length of the element as it is, and differentiation of constant will become 0. Therefore d zeta divided by dx is equal to 2 divided by le. Therefore dx divided by d zeta is reverse of this, that is le divided by 2. So remember this relation which is required, I need to substitute in the equation number 2. Similarly, my equation number 2 consisting of the value of d square v divided by dx square. Now in my entire equation number 2 is in the form of global coordinates. Now I need to convert that in terms of local coordinates, because I know the limit for the local coordinates. Therefore it becomes very easy to solve that integration. Therefore this d square v divided by dx square can be written like this using chain rule: d square v divided by d zeta square into d zeta square divided by dx square, where d zeta square will be get cancelled, left out with d square v divided by dx square, the same term. Now d square v divided by d zeta square, I'll keep it as it is. D square, d zeta square divided by dx can be written d zeta divided by dx whole square. Now I know the value of d zeta divided by dx from the previous equation, that is 2 divided by le. So let us substitute that value of d zeta divided by dx as 2 divided by le and this whole square as it is, and that will be equal to d square v divided by d zeta square as it is, then squaring these two terms, so it is 2 square, it is 4, and this is le square. So let us take this as an equation number 4. Now substituting the value of this d square v divided by dx square, and changing this dx in terms of d zeta, that is just divided by and multiplied by d zeta, so that I can substitute that value of dx divided by d zeta also into this. Therefore this entire integration will be in terms of d zeta. Therefore I can apply the limit. Earlier it is over the length of the element. Now as I have converted everything in terms of zeta, now the limit for zeta we know it is over the -1 to +1. Therefore 1 divided by 2 ei integration -1 to +1. Now the value of d square v divided by dx square is now converted in terms of zeta. That is the value I'll substitute here, and it is whole square is there. D square v divided by dx square whole square is there. I'll keep that whole square as it is. Then this into dx is there. That dx I'll convert in terms of d zeta by just dividing and multiplying. So therefore I'll get dx divided by d zeta into d zeta. So in the next I'll apply this square to both the terms here. So it is 4 divided by le square whole square and d square v divided by d zeta square whole square, and dx divided by d zeta I know the value of that from equation number 3, which is le divided by 2. Therefore I'll substitute that value as le divided by 2 into this d zeta as it is. Now the strain energy equation is equal to same thing, 1 divided by 2 ei integration -1 to +1, this term d square v divided by d zeta square whole square as it is. Then applying this square to both the terms here, so it is 4 square 16, le square becomes le raised to 4, and this le divided by 2 as it is, and it is d zeta. Now this entire integration now it is with respect to d zeta. Therefore we have substituted the limit -1 to +1. So in the next, the final equation I am going to get. So here in this relation I am going to take 16 le raised to 4 divided by into le divided by 2 as a constant outside. By simplifying it, so it is cancel the term here, it becomes 8, and this le 1 and 1 le you will be get cancelled, left out with le cube. So therefore when I take it outside, it is 8 ei divided by le cube 1 by 2 as it is. So that is what I am going to get, 1 by 2 8 ei divided by le cube integration -1 to +1, this d square v divided by d zeta square whole square into d zeta as it is. Now I need to differentiate the v. There v is the displacement in the beam, as y is replaced with v is the displacement in the beam. So this displacement in the beam I need to differentiate twice. Then whatever the value I am going to get, that I need to integrate with respect to zeta. So this is the beam element where I have shown the displacement in the beam, the two vertical displacement v1 and v2, and the two slopes, that is theta 1 and theta 2, where the node number 1 is at a distance of x1 in global coordinates, and the node number 2 is at a distance of x2 once again in global coordinates, where in local coordinates node number 1 is at zeta is equal to -1 and node number 2 is at zeta is equal to +1. Now in the previous session we told that the beam is subjected to the 3 degrees of freedom at each node, but here we have shown only the 2 degrees of freedom, and another degrees of freedom, that is in the axial direction, that we are going to consider in the later stages, because for a simple bar element we already done the axial displacement stiffness matrix, so you can add that in the later on stage. That is what the note I have given. We will first consider only the transverse displacement and the slope, and we will include consider the axial displacement later. We do this because in bar elements we already accounted for the axial displacement. It will be simple matter to include that effect later. Now v is the displacement in the beam, and we'll differentiate this v with respect to d zeta, so it should be d zeta. So here I am differentiating with respect to d zeta because everything I am considering in terms of local coordinates. Therefore I'll substitute this with respect to d zeta. Therefore I am going to get the slope for that equation. Just I'll change this to zeta instead of x. This I am going to change it to d zeta because everything now I am doing with respect to d zeta. Okay. This is what The v is the displacement in terms of d zeta, and differentiating this v with respect to zeta, I am going to get the slope. That is what v and dv by d zeta are the transverse displacement and slope in the beam respectively. Therefore, if at all I want to find out the displacement at any random distance in the beam, I need to take the help of the shape function. Therefore, that is I have mentioned here, the displacement in the beam v is equal to n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 2. This is the equation. By knowing the displacement at the nodes, that is v1 theta 1 v2 theta 2 are the displacement which are there at the node, and n1 n2 n3 n4 are the shape function. With the help of this, I can find out the displacement in the any random distance in the beam, where v1 is the displacement at node number 1, theta 1 is the displacement at node number 1, theta 1 is slope at node number 1, v3 is the displacement at node number 2, and theta 2 is the slope at node number 2. Now the shape function n2 and n4 are related to the slope, and the slope will be in terms of radians. Therefore, this v equation to be uniform in the units, when this v should be uniform in the units, therefore this n2 and this n4 should be multiplied with le by 2, so that the entire equation will be consistent with the units. Therefore, now I'll multiply n2 with le by 2 and n4 also with le by 2. Now this equation I'll represent in the form of matrix, because FEM deals with in the form of matrix. So let us put that in the form of matrix. That is n1, all these displacement I'll take it outside. Then it will become n1 le by 2 n2 n3, and this is le by 2 n4, and this is v1 theta 1 v2 theta 2. When I multiply this matrix and then open, I'll get the same equation. It is n1 into v1 plus le by 2 n2 into theta 1, same thing, n3 plus n3 into v3, this should be v2, this should be v2, so n3 into v2, then le by 2 n4 into theta 2. So this is what the equation I am going to get. Then this is what we call it as a displacement matrix. Therefore I'll just represent that as a v. This matrix as it is, this v1 theta 1 v2 theta 2 I'll represent in the form of v. Then I'll differentiate this v with respect to d zeta. Please remember, in my equation 5, I need to substitute the value of d square v divided by d zeta square value whole square. Therefore, let us differentiate this v with respect to d zeta. Therefore, d by d zeta of v is nothing but this equation. So I just substituted that equation. Take that equation as 6. Similarly, once again I need to differentiate that v with respect to zeta. Therefore, it becomes d square v divided by d zeta square. Therefore, d square divided by d zeta square into v, and once again this is what my v. Now, instead of substituting this entire equation in equation number 5, this is equation number 6, so let us take this as equation number 7. So substituting this d square v divided by d zeta square and differentiating this with respect to d zeta, then integrating it becomes very tedious process. Therefore, that we'll do in the form of matrix. How? D square v divided by d zeta square. Now v is in the form of matrix. So squaring a matrix, because this entire term I need to square it. So squaring a matrix is nothing but multiplying the matrix with its own transpose, nothing but it is squaring. Therefore, this d square v divided by d zeta square can be written as a d square v divided by d zeta square transpose with d zeta square into v divided by d square v divided by d zeta square. When I apply with the transpose, this is the matrix. This matrix will multiply with its own transpose, nothing but squaring it. Now you know d square v divided by d zeta square is this. Apply the transpose, and d square v divided by d zeta square is this. Now one matrix, first term is applied with the transpose and second term is without transpose. Now let us substitute this value of d square v divided by d zeta square means this term, nothing but this is the value. This value I'll substitute in equation number 5. So therefore I have 1 divided by 2 8 ai le cube integration minus 1 to plus 1 d square divided by d zeta square with this term applied to the transpose, and this is without transpose, into d zeta, because this entire integration is with respect to d zeta. I'll keep the d zeta as it is. Now in the next step I'll apply this transpose to each term here. Therefore it is this d square divided by d zeta square into this matrix with the transpose. This is the displacement matrix with the transpose, and once again this is the second term which is without transpose. Now I'll rearrange the terms in this equation. This equation I'll use and I'll rearrange the terms. When I rearrange the terms, 1 divided by 2 b transpose I'll take it outside the integration, then 8ai divided by le cube I'll take it inside the integration. Limit is minus 1 to plus 1. So this first term with transpose I'll keep it as it is. This is the second term without transpose, I'll keep it as it is with respect to d zeta, and this term is having v displacement matrix only v, that I'll take it outside the integration. Therefore this is the arrangement I have done with the same equation. Therefore if I see the above equation, strain energy is equal to half into v transpose into k into v. So this entire equation, from this integration to this with respect to d zeta, this entire integration will become k, that is stiffness matrix, because this is the strain energy equation which is we already studied, which is given by half into u transpose into k into u in bar elements. So same thing we have taken here. Therefore this entire equation of this integration is nothing but my stiffness matrix. So that is what I have written here, where k is integration minus 1 to plus 1, this entire relation. Now in the next step what I will do, I'll just apply the transpose to this first term, and this I'll keep it as it is. So where in the next 8ai divided by L cube as it is. Now first term is applied with the transpose. Transpose is nothing but converting this row into column. So this I need to convert into row into column. So therefore, and meanwhile I'll also take this d square divided by d zeta square multiplied with these all 4 terms, and here also. So d square into n1 divided by d zeta square, le by 2 constant outside, d square n2 divided by d zeta square, then d square n3 divided by d zeta square, then le by 2 constant outside, d square into n4 divided by d zeta square, converting into column, and after taking that d square divided by d zeta square inside the this matrix, this is the 4 terms I am going to get. Now I need to do the matrix multiplication here. So that is what I am doing, the matrix multiplication. Before doing the matrix multiplication, let us substitute the value of d square n1 divided by d zeta square. I know the value of n1 in terms of zeta, that is what my shape function for node number 1 for vertical displacement, n2 is the shape function for slope at node number 1, n3 is the shape function for vertical displacement at node number 2, and n4 is the shape function for slope at node number 2. So let us integrate this n1, because we know n1 in terms of zeta. So let us differentiate this n1 with respect to zeta twice. So this is my n1 equation. If you remember my first session, there we had derived all the 4 relation for shape function. So it is 1 divided by 4, 2 minus 3 zeta plus zeta cube. When I differentiate it first time, 2 is the constant, becomes 0. Differentiation of minus 3 zeta is minus zeta, minus 3, then 1 by 4 outside as it is, and differentiating zeta cube is 3 zeta square. This is one time differentiation, because I need to substitute d square n1 divided by d zeta square, means I need to differentiate n1 twice. Once again this I'll differentiate it once again to get d square n1 divided by d zeta square. So 1 by 4 as it is, 3 is a constant, 0. The differentiation of zeta square is 2 zeta, but already 3 is there, therefore it becomes 6 zeta. Therefore the final value is 6 zeta divided by 4, and after simplification I'll get 3 zeta divided by 2. This is the entire value of d square n1 divided by d zeta square. Similarly I need to differentiate n2 twice, so that is I have done here. So n2, we know this is a shape function for slope n2. Once if I differentiate, I'll get this, where 1 is constant, zeta is 1, zeta square is 2 zeta, zeta cube is 3 zeta square. Once again differentiating, 1 is constant, 0, then I left out with minus 2, and once again this is 6 zeta. So this is the value of d square n2 divided by d zeta square. Similarly, another 2, that is n3, I need to differentiate twice. So this is 2 constant 0, this is 3, then it is 3 zeta square. Once again differentiating, 3 is constant, it becomes 6 zeta. So when I simplify, it will become minus because it is associated with negative sign. So I'll get minus 3 zeta divided by 2. Similarly, differentiating n4 twice, I am going to get 1 divided by 2, 2 plus 6 zeta. Now substituting all these 4 values into the equation, therefore everything is same, integration minus 1 to plus 1, ai divided by le cube. Now this is value of d square n1 divided by d zeta square. Similarly here also this is the value of d square n1 divided by d zeta square, and this is the value of d square n2 divided by d zeta square. Similarly here, and this is the value of d square n3 divided by d zeta square, and that is the value here, and this is the final value, that is d square n4 divided by d zeta square. So that is the value I substituted here, therefore this should be dn4 divided by d zeta square. So that is the value I substituted here. Now next is I need to do the matrix multiplication. So you know how to do the matrix multiplication. The first row first column, first row second column, first row third column, and first row fourth column. So that is what I am going to get the values in the first row. So that is I am doing here. So same equation I have continued here. What is I have obtained in this equation I have continued here. Now when I multiply the first row first column, 3 into 3 it is 9, zeta into zeta it is zeta square, divided by 2 into 2 it is 4, means it is 9 zeta divided by 4. So it is 9 zeta square, sorry, zeta into zeta it is zeta square, so 9 zeta square divided by 4. So like this I'll show the first row values. Similarly you can do for the remaining. So next is 3 zeta divided by 2 into this second term. So 3 le zeta, 8 into 2 it is 16. So it is 3 zeta le divided by 16 into this minus 2 plus 6 zeta as it is. Then first row third column, it is 3 into 3 it is 9, zeta into zeta zeta square, and 2 into 2 it is 4. So negative sign is there, so that negative sign as it is. Please remember, while doing the multiplication, please don't forget to consider whatever the sign they are associated. Then the last term, it is once again 3 le zeta into 2 plus 6 zeta divided by 2 into 8 it is 16. So this is what my first row values. Similarly next what we need to do, second row first column, second row second column, second row third column, and second row fourth column, I'll get these values. Similarly you do remaining third row with all the columns here and fourth row with all the column here, I'll get this third row values and this fourth row values. Now once this is done, I have taken the same matrix here. Then what I need to do, if you see this matrix, here in this matrix, finally I need to integrate that with respect to d zeta. When I want to integrate, here I have some of the terms. Either I have to integrate zeta square, because 9 by 4 is a constant. I have to integrate with respect. This integration is applied to all the individual terms here. Whatever the terms I have here, all the terms I need to integrate with respect to zeta. So if I look in these terms, either I have a zeta square, or I have a zeta, or I have a constant. So only these three possibilities are there. Therefore outside only let us calculate what are those values. Then in the next step, directly when zeta square is there, directly I can substitute that integrated value. So when I integrate zeta square with respect to d zeta, it is zeta cube divided by 3. Apply the limit minus 1 to plus 1. When I apply the limit and I simplify, I'll get 2 by 3. So in this matrix, wherever I have zeta square like this, there I can directly substitute the value as 2 by 3. Similarly, I have also zeta. When I substitute that zeta and I integrate, the integration of zeta is zeta square by 2, apply the limit. When I simplify, it becomes 0. That means wherever I have zeta, this term directly I can make it 0. And I have a constant also. So integrate the constant with respect to constant will become zeta. When I apply the upper limit minus lower limit, the value is 2. So in the next case, what we'll do, wherever zeta square, please remember, wherever zeta square I need to substitute 2 by 3, wherever I have zeta I need to substitute 0, and wherever I have constant like this 4, I have minus 4, I have 4 here, I have minus 4. So wherever I have constants, there I need to substitute the value as 2. So that is what I have done. After substituting all those values, this is the value I am going to get. I'll show it for the first one. So here only one term I'll show it, same thing you can do it. So 9 by 4 as it is, the value of zeta square is 2 by 3. When I substitute it 2 by 3, so it will become 3 by 2. It becomes 3 by 2. So that is what I have written. And meanwhile, what I have done, I have taken this E to inside the matrix, and this E is this 8 is multiplied with all the terms inside the matrix. Then after simplification, I'll get this matrix. Further simplification, I'll get the final matrix. So this is what my final matrix, stiffness matrix for the beam element. Same thing. The first term, if I take it, it is when I solve this, so this will be 12. So it is 2 ones are 2 4s are 4 3s are 12. So that is first term. Similarly, when I solve this, it is 8 ones are 8 2s are, and 2 ones are 2 6 are. So it is 6 LE. So it is 6 LE. Similarly, this term it is same, only it is associated with negative sign. So I taken minus 12, and this term it is same. Therefore, it is 6 LE. So these are the first row values. Similarly, you simplify second row, third row, and fourth row. Similarly, I'll get second row, third, and fourth row values. Please remember, these two, this is negative, and these two and this is negative. This middle 12 is positive. So this is the stiffness matrix for the beam element. Now, as I told, we have considered only the two displacement at each node, but it is subjected to the 3 degrees of freedom at each node. Therefore, I have considered two noded beam element. Therefore, totally 6 degrees of freedom. Therefore, let us consider the two more which I am included now here. Earlier, I have only V1 theta 1, V2 theta 2. Now I included U1 V2. U1 U2, I included U1 U2. Those are the two axial displacement. Therefore now at each node I am having 3 degrees of freedom. Therefore totally 6 degrees of freedom. For time being, if I neglect V1 theta 1, V2 theta 2, now it becomes a simple bar, one dimensional bar subjected to the displacement are degrees of freedom, 1 degrees of freedom at each node. For that I already derived the stiffness matrix, that is given by AE divided by LE. 1 minus 1 minus 1 1 is the matrix. I'll take this A divided by LE inside the matrix. Therefore, this is the matrix I am going to get. Now, let us give the number so that I can take that. U1 is nothing but 1, V1 is nothing but 2, theta 1 is nothing but 3. So, I'll give the number. Accordingly, I need to add those two matrix, that is stiffness matrix, what I obtained for only 2 degrees of freedom, and this is only 1 degrees of freedom that I need to add. Therefore, I'll get the stiffness matrix for all the 6 degrees of freedom. Similarly, this is 1 2 3, this is 4, this is 5, this is 6. So totally 6. Therefore U1 U2 are associated with 1 and 4. So I have taken 1 4 1 4 vertically, horizontally I have mentioned, horizontally vertically I mentioned 1 4. Then this is 2 3, then this is 5 6. So 2 3 5 6, that is what I have mentioned for the 2 3 5 6 for the 2 degrees of freedom what I consider for the beam element. Now when I add this, so 1 of 1 here, 1 2 3 4 5 6 vertically, and this is horizontally. When I add 1 of 1, it is A divided by LE. 2 of 1 0, 3 of 1 0, 4 of 1 I have minus A divided by LE. So that is 1 of 1, it is A divided by LE, 1 of 4 is A divided by LE, 2 of 4 everything it is 0. So that I have mentioned. 5 of 1 is also 0, 6 of 1 is also 0. Like this you add these two matrices. These are the two matrices I need to add. This is the first matrix and this is the second matrix. When I add these two matrices, I am going to get the stiffness matrix for 6 degrees of freedom. So this is the stiffness matrix for 6 degrees of freedom. Thank you for watching.